Hello. In this presentation, we'll be discussing nonlinear optics of photonic hypercrystals, optical limiting, and hypercomputing, which is supervised by Professor Anshuman Kumar under the course PH 421. Our goal is to achieve enhanced photon-photon interaction for application in optical computing. Photonic hypercrystals combine the most interesting features of hyperbolic metamaterials and photonic crystals. Since the dispersion law of extraordinary photons in hyperbolic metamaterials does not exhibit the usual diffraction limit, photonic hypercrystals exhibit light localization on deep subwavelength scales, leading to considerable enhancement of nonlinear photon-photon interaction. Nonlinear optics of photonic hypercrystal is such that one of the spatial coordinates would play a role of effective time in a 2 plus 1 dimensional optical spacetime. Mapping the conventional optical computing onto nonlinear optics of photonic hypercrystals results in a hypercomputing scheme which may considerably accelerate computational time. Hyperbolic metamaterials and photonic crystals. Photonic crystals are periodic dielectric nanostructures with changing refractive index, whose period is of the order of optical wavelength. Hyperbolic metamaterials are artificial materials with positive dielectric constant in one direction and negative in another, leading to a hyperbolic dispersion relation. Now, mitigating loss in hyperbolic metamaterials. Hyperbolic metamaterials experience losses. The solution is to integrate gain media as a dielectric component, and the result is lossless and potentially active hyperbolic material. What are photonic crystals? They are periodic dielectric nanostructures with changing refractive index. Their period is of the order of optical wavelength. Now, what are hyperbolic metamaterials? The metamaterials with hyperbolic dispersion relation are hyperbolic metamaterials. We also introduce analogy to gravity. The z-axis can be treated as a time-like axis in a 2 plus 1 dimensional optical spacetime. Quantum computers require qubits or quantum bits. Single photons are a promising candidate. Firstly, they can encode in polarization path and time beam. Secondly, they're free of noise. Challenge: strong enough nonlinearities for this conditional shift for single photons is not available. The reason is the Kerr effect. The nonlinearity of materials is proportional to intensity. Example, refractive index is equal to N0 plus N2 into intensity. Single photons results in less intensity, which results in no nonlinearity. A way out in this situation is increasing intensity or photon interaction at single photon level. Intensity is inversely proportionate to volume. Intensity increases if volume decreases, so we need smaller volumes. Recent research suggests that photonic crystal-based ultra-small mode volumes are being used. Nonlinearity is observed at single photon levels. Why photonic hypercrystals? Conventional diffraction limit is very less than the wavelength of light. Rd is equals to period of the crystal being very less than the wavelength of light indeed. So diffraction should occur. But the twist is dispersion relation of hyperbolic metamaterial for extraordinary photons does not exhibit conventional diffraction limit. Therefore, Bragg scattering of extraordinary photons results in formation of photonic band structure no matter how small L is. Therefore, photonic hypercrystals exhibit light localization on deep subwavelength scales, which far exceeds the demonstrated mode volume reduction in photonic crystals. So our goal is proving that nonlinearity time-like z-axis of hypercrystal relation is useful in optical limiting that is limiting the intensity of light, and optical computing.
Let us now look at the structure of our photonic hypercrystal. We know that the photonic hypercrystal is composed of an artificial hyperbolic metamaterial as well as narrow layers of a dielectric medium. So, in our case, we're using porous alumina filled with silver nanowires as our artificial hyperbolic metamaterial. The silver nanowires act as the conductor while the alumina acts as the dielectric medium um, or the insulator. This exhibits a low loss type 1 hyperbolic behavior in the visible range. What does this mean? Low loss means that the loss is low, while type 1 means that the dielectric constant in the x and y directions, that is in two directions, is positive, while the dielectric constant is negative in one direction. In a type 2 material, we have the dielectric constant being negative in two directions and positive in one direction. Clearly, a type 2 material is more metallic in nature and is hence more conductive and reflective as compared to a type 1 material. Now, in our material, we've chosen these particular material parameters. That is, our epsilon x is equal to our epsilon y, which is equal to epsilon 1, which is 5.28, and our epsilon z equals epsilon 2, which is negative, which is minus 4.8. And these dielectric constants are at 660 nanometer wavelength. Now we want to assume that epsilon xy is equal to epsilon 1 or 5.28 throughout the crystal. This is a valid assumption to make because we choose our dielectric layer between the hyperbolic resonators in order to satisfy this criterion. So we notice that the square root of epsilon 1, which is 2.3, nearly matches the refractive index of lithium niobate, which makes this a good candidate for the thin dielectric layer. Now, to counter losses in the silver based hyperbolic metamaterial in the visible range, we consider using an RH800 dye doped dielectric polymer as a gain medium, um, since we want the overall net loss to be zero. One solution to mitigate the loss in our case is to use a 660 nanometer wavelength saturated dye in porous alumina. Additional to the dielectric medium, the dye, and the hyperbolic metamaterial, we also have grating structures which are embedded within these hyperbolic resonators for controlled nonlinear photon-photon interaction. Let us now look at a figure to understand everything that we have discussed. Um, as you can see, there's a alumina based hyperbolic metamaterial separated by thin layers of nonlinear dielectric medium, lithium niobate. And in the hyperbolic metamaterial, we have a buried grating, which is actually at a 45-degree angle to both the x and y axes in the xy plane. Since we use the direction of propagation of our light, that is either kx or ky, to encode the bits 1 and 0, this buried grating can be turned on and off to control the optical bit mixing. A suggested improvement for the photonic hypercrystal structure is to use natural hyperbolic materials, as they would be cheaper to fabricate and more efficient to use. Pure alumina is one such candidate, but the problem is that it only exhibits this low loss hyperbolic behavior of type 1 in the long wave infrared range. And in this long wave infrared range, we see that the dielectric constant in the x and y direction is equal to the dielectric constant of Z and Se, and so Z and Se can be used due to its high transparency. Um, we would also require single photon detectors, and since of late we have been able to find long wave infrared regions in single photon detectors, we could actually consider using natural hyperbolic materials to make our photonic hypercrystal. One interesting thing to note is that in a uniaxially symmetric medium, such as our photonic hypercrystal. Um, the transverse electric and transverse magnetic polarized modes. Um, sorry, the ordinary and extraordinary waves actually just reduce to transverse electric and transverse magnetic polarized modes. What does this mean? So, ordinary waves have their electric field perpendicular to the ray path, while this is not the case for extraordinary waves. That is, that they have some component of electric field in the direction of the ray path. Let's say we have a plane wave that is propagating in the z direction, and its electric and magnetic fields are some functions of z. Then, as they approach a narrow medium, or actually any medium that cuts off the plane waves, we see that the waves actually change their direction of propagation. Um, and if we consider a wave, so let's say that the new direction of propagation is along this line given by k1 and k2, then our new electric and magnetic fields for the two waves become functions of this k1 direction and k2 direction. Now let's say that we have in we are considering a plane wave wherein the electric field is perpendicular to the direction of this medium. In that case, the electric fields of the two waves add in the out of plane direction trivially, and we get some E of k1 plus E of k2. But the magnetic fields, since the value of k, since the radial distance of k1 and k2 from the point of origin of these waves are different, we see that BE of K1 and BE of K2 add non-trivially and have a component along this general K cap direction. And this means that there is some magnetic field component in the direction of propagation of the wave. Um, while if we have the magnetic field perpendicular to the plane and have an electric field in the plane, we see that the electric field has a component which lies in the direction of propagation. Um, if depending on which component is out of plane, we call these waves transverse electric or transverse magnetic. Clearly, in the transverse electric waves, we have no electric field component in the k direction, which makes these ordinary waves, while in the transverse magnetic waves, we have some component of the electric field in the k direction, which makes these extraordinary waves. Now, for the mathematical analysis, we have Gopal.
So now we go into the mathematics of this paper, and we start with the macroscopic Maxwell equation, which can be that del cross equals to omega square by c square into displacement vector. As we expand this del cross E into in terms of I, J, and K, we find this kind of expression. Now, for the extraordinary part, Ex is zero. For extraordinary part, the electric field is only in the direction of Y and Z, and so del cross E becomes this. Now, another well-known thing is that del dot D equals to zero since there are no charges and all induced. So, and the displacement vector can be given in terms of electric field and the dielectric permittivity tensor. So, uh, del dot d we do del dot equals to this. This del is just a typo, and we find the relation between del ey by del y and del ez by del z as this. Now, we equate the z component of del square equals to this Maxwell equation, omega square c square displacement vector, only the z component, and we now substitute the relation that we have found between ey and ez uh, here. Yeah. So this is what we found after the substitution. Now we say that Ez equals to psi. This is our extraordinary photon wave function. This is only Ez and no components from Ey and Ex. Epsilon y and epsilon x. This is only epsilon z actually. Okay. Yeah. So the equation that we find is this now, and this is very similar to 3D Klein-Gordon equation where two spatial dimensions are there, and one is the time dimension. See, del square and t. Okay, this is the del square and this is the t. So z is actually acting like a effectively a time axis. And the dispersion law of extraordinary waves in HMM can be given by this, as we all know. And the volume between two such hyperboloids, like for different frequency, there will be a different hyperboloid, and the volume between those two hyperboloids is basically infinite. And between two frequencies, infinite values of k z can lie, which leads to infinite density of photonic states in HMM. That is how many kz can exist. So now we consider behavior near Al2O3 and lithium niobate boundary. Earlier you were considering only in the bulk of HMM. And epsilon xy is epsilon 1, 5.28, which is constant throughout the crystal. Now, since there is translational symmetry in x and y direction, kx and ky can be taken as good quantum numbers. However, kz can't be taken as that good because it changes. Epsilon z is changing and it changes. So propagating wave we can write in these terms. We just separate out the kx and ky part as they are good quantum numbers, but we put Ez in this functional form only. Similarly, displacement vector wave and the magnetic field can be written as this. Now, the Z component of the electric displacement vector of the transverse magnetic wave. We take the transverse magnetic wave's electric displacement vector and only its Z component, like we did earlier. We took only Ez in the bulk. Now we are taking the dz, where Ez is also there. So Ez is multiplied to this. So for this case also, del dot d equals to 0. And now we can't take Ez, epsilon z outside because it depends on z. So this is psi. And now we can write del e y del y equals to minus 1 over epsilon 1 del psi by del z. So equating the z component of the Maxwell equation again, we find this expression. And earlier we had the expression for Ez as this, for the electric field as this, and now we say that it's kx square plus ky square times Ez minus 1 upon epsilon 1 del 2 psi by del z square. This can be substituted here. Now the differential equation that we have is here, and we are saying k we are saying kx square plus ky square equals to k square. This is very similar to a time-independent Schrodinger equation where we have a periodic potential epsilon 1 k square upon epsilon z. So this is a very well-known problem in quantum mechanics, and this is solved using Bloch's theorem. So what does Bloch's theorem says? Bloch's theorem tells us that if we have a differential equation of this form, where V z is a periodic potential, then the solution can be given by this. Solution can be expressed in form of u, and u which is a periodic function with same period as multiplied by e raised to power I k z. And since the u is a periodic function, our psi follows this condition. Now we introduce the boundary condition, which says that the wave function at the boundary and the starting point is actually both the boundaries are equal. So, and n is the total number of periods in the crystal. From this, we will find that kz can takes kz into z can take 2, and kz into kz times n l can take only integer multiples of 2 pi. So U can be written in term use a periodic function. It can be written in terms of Fourier series as this, and we just substitute it here, and this is our expression for psi, where kz is can be given by this. This could be found by boundary condition that impose. So since our psi z follows this condition, we need to solve only in region z equals to 0 from 0 to L. For other z's, it can be found out by this relation. So for large n, kz will go beyond pi, but we want k into z, kz into z actually. This is a typo. Kz into z from minus pi to plus pi. As the other solution will be just redundant, it will just 2 pi, as we add just 2 pi plus x face reduces to x, it is just that kind of thing. So, and since z is between 0 to L, kz can go from minus pi by L to plus pi by L. So this region in kz space is called the first Brillouin zone. And so we can express psi z in terms of kz and is this summation. There should be a psi m constant multiplication for each term. Yeah. So near these boundary values, kz equals to pi by L, we see construct strong Bragg scattering, that is constructive interference. And this will lead to photonic band gaps in both wave number and frequency domains. Band gaps just mean that which values of frequencies are allowed to propagate and which are forbidden, which are not allowed. That is called the forbidden region. So, since the potential contains epsilon z, we need to find out what is the form of epsilon z so that we can find out the form of potential. So, epsilon z near one of the interface we are expressing as this. Okay, we are saying that z equal to 0 is an interface, and there are no other interfaces right now, only one interface, and epsilon z can be given as this term. We assume this such a form because we assume that the extreme values of epsilon z, epsilon like in the crystal, in the bulk, it remains in the bulk of HMM, hyperbolic metamaterial, which is alumina, it remains as epsilon 2, and in lithium niobate dielectric, it remains as epsilon 1 constant, right? So we assume that it approaches both these values in these materials asymptotically. That's why we took a form which makes effective potential like this. Here, the delta is the transition layer, which is very small, and gamma is the imaginary part of epsilon z, okay, which is very small than 1. It's just 0.424 we have assumed. Now, the effective potential can be given by this after assuming such a form of epsilon z. See, it diverges, so it's like a potential barrier or potential wall. For like all the interfaces, this can be given as this. The potential can be potential looks like this. Now we assume that gamma is much less than 1, and so we take only the real part of epsilon z, and we do a change of variable, saying that u is exponential psi by delta. So the potential form in terms of epsilon 1 by epsilon z in terms of u can be given as this. So our differential equation is this, and we have made a substitution. We have made a change of variable. Now we want del to psi by this differential equation in terms of u rather than z. So we just do trivial substitutions and find this. So our differential equation after putting the values of after putting the functional form of epsilon z and making a change of variable to u. This is our differential equation. This is somewhat different from the what we have found in the paper, but the solution that we reach is exactly with this equation is exactly the same as given in the paper. So we assume this is a differential equation only. And now we express our differential equation in this form, where A can be expressed in terms of delta omega epsilon 1 and k, and similarly B can be expressed in that form. So this equation can be converted into this form. We want to convert it into this form by it can be done using some substitutions, which we are not going to show. And because we want such a form, because this the solution of this differential equation is actually a hypergeometric function, which takes three arguments a, b, c, and the variable z x, which is here. So what are hypergeometric functions? Hypergeometric functions are a very general class of functions, and many trigonometric functions, Bessel functions, and Jacobi elliptical functions can be expressed in that hypergeometric functions. So how is hypergeometric function represented? This is 2f1 is the representation, and it takes three constants as arguments and one variable that it is, and this is the form. It can also be expressed in gamma function, which looks like this. Now, our solution of psi in terms of this hypergeometric function, which can be found out by just putting that differential equation, this differential equation into some sorry, wait a second. Okay. So this can be put into some differential equation solver like Wolfram and something like that. You will find the differential equation solution can be given it is given as this in terms of hypergeometric functions. And one of the first part is the this is the incident part of the wave. Second part is the reflected part of the wave, and R is the reflection coefficient. So at the interface, we assume it's a very high potential barrier, so psi is equals to 0, and the reflection coefficient R can be found out from this, putting 0 here. So R will be just U will be 1 at Z equal to 0. We Psi is equals to 0. So this is what R is, and it too can be expressed in terms of gamma functions as well. And in the limit where gamma is much less than 1 and a equals to 30 and b equals to 40, this we take some values of a and b, we find that the intensity diverges at the interface, sharply diverges and decreases. What it means that why it happens is because of the lightning rod effect of the tips of silver nanowires. At the interface, the silver nanowires end, which are in the hyperbolic metamaterial, and at the interface, lithium niobate is going to start. So there are divergence, and after that, the electric field decreases sharply. So now we introduce space-time interval, optical space-time interval. So we know that in special relativity, the space-time interval can be given by this, and optical space-time interval we are giving in the same terms where z is the effective time, and we have a scale factor actually here. Here you can see the scale factor in space-time interval is just 1, and now we have a scale factor minus epsilon 2 by epsilon 1 raised to power half. This is just a scale factor. Now this scale factor is not constant, as epsilon 2 is a function of epsilon z is a there should be epsilon z. This is a function of z actually. So as this will change with z, okay? So we can see it looks something like this. So what is that the effective scale factor emerges and then remains constant for some time, and then again goes to 0. So this is actually Big Bang and Big Crunch. These are the anomaly that create that it is the birth of space-time and the destruction of annihilation of, you can say, the space-time, which is called Big Crunch. At the interfaces, we observe Big Bang and Big Crunch. And this inflation-like behavior of the effective scale near the interface leads to extremely large field, extremely large intensities, and this will cause strong non-linearities at interface because we know that non-linear effects kick in when there is large intensity. And these strong non-linearities will turn the grating on, which is in the lithium niobate layer, if it is very close to that grating, then it will non-linearity, that intensity is high near the grating, then it will get turned on. And now um, um, this activated grating can alter the state of the signal photon. If the grating is off, if there is no high intensity, no grating turned on, then it won't be able to alter the state of photon.
Uh, Section, we'll be looking at various plot that we have plotted in Google Colab. So first plot is epsilon z versus distance. So we know that epsilon z is a dielectric constant along z-axis, and as hypercrystal is made up of hypermetamaterial and dielectric, we know that epsilon z value in hypermetamaterial is negative, which is minus 4.8, and for dielectric it's positive, which is 5.28. So when we plot our epsilon z versus distance, we will see the behavior as follows, which is negative in hypermetamaterial region, then positive in dielectric. And as hypercrystal is made by periodic arrangement of hypermetamaterial and dielectric, we will see epsilon z behavior as follows. So let us move at our next part, which is effective potential. Now, as discussed by Gopal, when we see at this equation and compare it with Schrodinger equation, we'll see that here this epsilon 1 by epsilon z is equal to effective potential. So um, and epsilon z here is this expression. Now for hypercrystal made up of Al2O3 and which acts as a hypermetamaterial, and LiNbO3 which acts as a dielectric. So here tau is much less than 1. So we can neglect this imaginary part and focus on real part, as this value is very close to 0. So when we put our effective potential epsilon 1 by epsilon z, we will see the potential as follows. So the speciality of this function is there is a large deviation near the interface. This is because when we look at our epsilon z function, here the e to the power z by delta. Now delta here is so small, and when the value is very close to 0, this tends to infinity. So when we plot our effective potential, therefore we see a very large deviation. Now the next graph is just extension to a hypercrystal, which is like it's just a periodic arrangement of hypermetamaterial and dielectric. So we can see it decays here and then sharply rises. There is a large deviation as we move from hypermetamaterial and dielectric, and as follows. So let us look at our next graph, which is effective scale factor, which is equals to minus epsilon z by epsilon under root of minus epsilon z by epsilon 1. So when we look at our expression epsilon z, we know that in hypermeta material, epsilon 2 is negative. So effective scale factor, which is minus epsilon z by epsilon 1, this when in hypermeta material becomes positive. So when we plot our graph, we see a sudden decay here, and as we move in a dielectric region, we know that epsilon 2 is positive. So here we can't define a effective scale factor. So that's why in this dielectric region we have considered it as a 0. And another time as we move in a hypermeta material, it exponentially rises here. And as we move to another dielectric region, we see it as a zero. So this is a plot for effective scale factor and distance. So next comes our intensity graph. So as discussed by Gopal, when we solve our hyper geometric function, which is this equation, and where a represent this and b represent this, and u is e to the power z by delta. So when the solution for geometric function comes out to be this expression, and uh, here psi of u is a displacement vector, and when we divide our psi of u with epsilon z, it gives us electric field. And when we square our electric field, this gives you intensity. So when we plot our intensity function, it comes out to be as follows. Now the speciality of this plot is when near the interference of hypermetamaterial and dielectric, we see a sharp rise in intensity.
Let us now consider how the introduction of photons into the individual hyperbolic resonator alters the effective potential, that is B equals to epsilon 1 by epsilon c. So we know that EG wires along Z direction, sub setup is like this, that we have already explained. The diagonal components of the probability tensor of the wire as a metamaterial may be obtained as B's relation, that is given by epsilon 1 approximately equal to 1 plus alpha by 1 minus alpha into epsilon d, and epsilon 2 is equals to alpha em plus 1 minus alpha ed, where alpha is the volume fraction of the metallic phase, that is of Ag wire, and epsilon for metal is negative expected, and epsilon d is greater than 0. So now we'll assume that the non-linear optical interactions do not affect epsilon m, because we assume electric field should not penetrate inside metallic phase. So now what is the main effect of non-linearity? So the dielectric components of Al2O3, Li and BO3 will be influenced by interfacial electric field divergence that we have discussed in our previous plots, via the non-linear curve effect that is given by n is equals to n0 plus n2i. So we may assume asymptotic behavior of n2 at the interface, and we can approximate it using n2z is equals to this equation, that is n2 plus e to the power z by delta 1 plus exponential z by delta, where delta is our transition length. Here we have taken as an assumption, and that is in general true, that n2 plus is in general very very greater than n2 minus. So we can neglect the effect of n2 minus. So as we are discussing the main effects of non-linearity, so main effect of non-linearity will be shifting the position of potential wall. The effective potential in the presence of photon field may be estimated as follows. It is Vz is equals to epsilon 1 by epsilon 2, where epsilon 1 and epsilon 2 are now a function of intensity. So we'll approximate it using Taylor expansion up to first order in intensity. That is equals to epsilon 1 plus 2 root epsilon 1 and 2i by epsilon 2 plus 2 root epsilon 2 and 2i. So we can again approximate this assuming epsilon 1 is very less than epsilon 2, that is in general the case. So we'll approximate it using the expression epsilon 2 by epsilon 2 plus root 2 root epsilon 2 and 2i. So we see that the form of denominator has changed. Therefore, we expect the roots of the solution should change. Therefore, the maximum and minimum of the solution will change. Therefore, the point of maximum and minimum of V of Z will change. So, point of divergence of V will also change. In some sense, they have shifted the position of potential wall. So, equation makes clear that the main effect of non-linearity consists of shifting the potential position of the potential wall. So, here we have shown two different cases: no light, that is intensity 0; 100 photons, intensity greater than 0; 300 photons, intensity kind of very greater than 0. So we see that for these three different kind of intensities, our position wall is not located at the origin. It is shifted away from origin as we go on increasing intensity. So what is the effect of positioning the potential wall? In a bit encoding scheme based on kxy direction, that is on based on polarization of our electric field, mode coupling properties of buried grating may be altered between on and off just via positioning the potential wall B, either in front or behind the grating. So, in the absence of control light, the 45 degree grating embedded in the non-inner layer is exposed, and therefore it mixes the 0 and 1 states in equal proportion. Under the illumination or under the presence of control light, the effective potentials move beyond the grating so that the optical mixing is switched off. Therefore, just by shifting the potential, we are turning on and off this mixing between 0 and 1 state. The second important effects of non-linearity is the effect of broadening of tunneling gaps. So control light may be used to drastically change transmission of photonic hypercrystal via broadening of tunneling gaps around the non-linear dielectric layer that we can show that we see in this picture. In the optical limiting scheme, intense light drastically changes transmission of photonic hypercrystal via broadening of effective tunneling barrier around the non-linear dielectric layer. That means seeing figure 2. If control light is turned on, our transmission will be severely affected because of broadening of tunneling length. Now, till now we haven't uh, discussed single photon interaction. To increase single photon interaction, we should increase non-linearity. So obvious way to increase non-linearity is to increase N2. So an obvious way to increase N2 by 2 or 3 orders of magnitude compared to LIMDO3 and to reach single photon level is to implement a photonic hypercrystal cavity design and make use of EIT effect, that is electromagnetically induced transparency effect, in either atomic impurities or quantum dots, as is typically done in conventional photonic crystal cavity geometry. Much higher levels of N2 nonlinearity are achieved due to considerably small mode volumes in such nanocavities. Considerable photon-photon interaction may be observed at a single photon level, just by increasing N2.
Yeah, so as we looked in the previous sections that the information can be encoded with the help of light via two methods. One is that either you encode information via intensity or with the help of the variables kx and ky of the wave. That is a wave number. And wave number proved out to be a good representation of optical bits. We can take some case like kx can act as a 0 and ky can act as 1. Now we talked in the previous section that there exists grating between the interfaces, and the grating, the role of grating is to mix the states and to uh, take out the individual states when it is required. So we talked that when the effective potential go like changes its position with the respect to the grating, it can change the state of grating whether it is on or off. And when the grating is off, we can see that there exists mixing of states, and states can be a combination of both of the state, like both of the bits 0 and 1. So let's take example that the grating state is at the angle of 45 degree. So with the at the 45 degree, the it will be the equal mix of both the state, both the optical bits. That is, both the bits will have probability of coming out half and half. And when we apply control light, the grating will get on and the mixing will not be there anymore. So this is the equation that we looked in the other section, and the psi in here represent the wave function of the photon that will be present in the crystal. Now, in the non-relativistic terms, we will see that the kinetic energy is much smaller than the effective rest mass mc square, and this equation will reduce to the Schrodinger equation, and the only difference the here will be the difference in the Hamiltonian operator, which will be something of this form. So we talked that uh, there exists some resemblance with the Minkowski spacetime, and we can see that it can be somehow shown as 2 plus 1d, where one dimension will be the time. Now, in our case, that z coordinate will act as the time. So, in the conventional computing sense, when we have to perform some computing steps, so we rely on clock cycles, and when the clock is high, the program will execute, and we have to depend for some amount of time. Like, let's say we have to take n steps of a clock, so we'll have to wait for n number of cycles, that is n by v
time, that where v is the frequency of the clock, and then only all those programmable steps will execute. But now what we are doing is we are saying that the time is no longer the time that we generally talk about. It will be the space. The z coordinate will act as a time. So we have a crystal of length L, so it will represent some amount of time simultaneously. Like collectively we can see a long period of time. So the n number of time steps will turn into n number of spatial steps, that is some length, and we can simultaneously perform the computing steps, like uh, as given here, that the control light A and B will act as the input and the X signal will act as the output. So here we are relying that these are the uh, if it would have been some like uh, normal computer, we will have to wait for this much amount of time, that is one, that is like 7 steps. We will have to wait for 7 steps to get these results, but the result in the X. But in the crystal, all these results will simultaneously execute, because the length will simultaneously show us the length of the time that we are talking about. So in this way we can have a very fast computing, which is much faster than the currently systems that are in existence, and we can somehow, it resembles to the very like the very new topic of faster than the light computing, because we can have a lot of computation steps at
Let us now discuss the potential limitations of the photonic hypercrystals. The large density of optical states in the hyperbolic metamaterials could imply reduced group velocity compared to the velocity of light in vacuum, which may impede the optical hypercomputing computation scheme. However, in hyperbolic metamaterials, the magnitude of group velocity is still very high and is approximately zero point 0.1 to zero point 0.3 times C naught, where C naught is the speed of light in vacuum. Information propagation time between the resonators, that is L by Vg, where Vg represents group velocity, is in the femtosecond range because of L being extremely small and in the deep subwavelength region. This far exceeds the gigahertz clock speed of both classical and quantum state of the art computers. So we can see that this speed is not really going to be an issue. Another issue that could arise is that of balancing losses. While too much propagation loss will make the individual optical bits non-interacting, too little loss may also lead to undesirable backscattering effects. However, we can tackle this limitation as well if we find if we properly choose our gain medium and the length of the individual hyperbolic resonators in the photonic hypercrystal structure. In conclusion, photonic hypercrystals exhibit light localization on deep subwavelength scales, leading to considerable enhancement of nonlinear photon-photon interactions. Furthermore, nonlinear photonic hypercrystals appear to be very promising in optical limiting and optical computing applications. Since the spatial coordinate plays the role of time in photonic hypercrystals, an optical hypercomputing scheme can accelerate the computation time greatly. Thank you.